All right, good afternoon, everyone. Welcome to lecture 25. We're learning about open channel flow today. So let me go over to the annotator and we'll start from there. And it's working. Wonderful. Okay, so as you can see, we're talking about open channel flow today. This is a topic that has lots of applications in civil engineering. I know there are a couple of you in this class who are civil engineers here at Tech. And we are talking about the first two sections of chapter 10. So just some general characteristics of open channel flow. And then the Froude number, which is a really, very, very important dimensionless number in open channel flow that is equally as important as the Reynolds number. And we'll talk about surface wave generation in open flows. And next time we'll talk about what can happen when we have surface waves. They can build up critically and cause a hydraulic jump. But for now, let's just have our introduction to open channel flow. So this, just walking around the way that we experience the world every day, if we look at fluid flows, these are the types that we're most likely to think of, right? So you see here, we've got a sort of channel winding through a water park. Here we've got a really regular looking channel. It looks like it's probably just uniform depth. There are no ripples on the surface, so it looks like a nice quiet flow. Maybe the water is even still. And then here we've got a spillway where we've got really rapidly varying flow and turbulent flow, as you can see. So the first classification we have with open channel flow is whether the flow is uniform, gradually varying, or rapidly varying. So if you look at this cartoon here, you see water exiting from a reservoir onto a spillway. And when it first goes from the reservoir onto the spillway, there's a rapidly varying portion here, right? As it really accelerates quickly, picks up a lot of speed, and then conditions don't change very much. So you've just got a uniform flow. And then we come up to a gate or a sluice, and the water backs up behind the gate and then tumbles over the top. So we've got regions of rapidly varying and uniformly varying. Here we've got gradually varying flow again, rapidly when the angle changes abruptly, and then uniform, right? So what does this mean mathematically for uniform flow? It means that there's no change in the depth, y, with x, the flow direction. For non-uniform flow, of course, it's the opposite. We do have a change in y with x. And then non-uniform flow could be further classified into gradually varying and rapidly varying, right? So gradually varying flow, we say that dy dx is much less than 1, right? So the change in the depth over the distance, if we go 1 unit downstream, the change in depth, it does not approach anywhere near 1 unit. It's much smaller, so at least an order of magnitude smaller. For rapidly varying flow, on the other hand, we have that dy dx approaches 1, right? So if we flow downstream 1 unit, 1 meter, then the change in depth is also on the scale of 1 meter. All right. Well, that's the first classification, but like any flow, we can also classify open channel flow as laminar, transitional, or turbulent, just like we did for pipe flows. When we calculate the Reynolds number for open channel flow, we use something called the hydraulic radius. as our length scale. Remember, for pipe flow, the Reynolds number, our length scale was the diameter of the pipe. Here it's the hydraulic radius. So just writing down the definition of the Reynolds number again, it's either rho v hydraulic radius over dynamic viscosity, or equivalently, it's the velocity times the hydraulic radius over the kinematic viscosity, right? Those are equivalent because the kinematic viscosity equals the dynamic viscosity divided by density. And then hydraulic radius is just defined as the area, let me actually stack that, the area, the cross-sectional area of our flow over the wetted perimeter. So let's draw a little sketch here. Let's say this is a channel cross-section. And let's say we've got a channel that's partially filled with water, but not completely. So the cross-sectional area is, again, the wetted area of the channel. And then the wetted perimeter, we just trace around, use a different color. We trace around the perimeter, but we only go so high as the water level, right? So for both the area and the perimeter. All right, and then we have a rule of thumb for whether an open channel flow is laminar, transitional, or turbulent, just like we did for pipe flow. Does anyone remember what our rule of thumb was for pipe flow? So if you have a Reynolds number less than something, you can assume that the pipe flow is laminar. Anybody remember? Yeah, about 2100, right? Thanks. And then above about 4000, you could assume that pipe flow was turbulent. So we have the same type of rule of thumb for open channel flow. So for a Reynolds number less than about 500, so you can see open channel flow is much more sensitive than pipe flow. However, the transitional period lasts for a really long time, right? So it's actually transitional from a Reynolds number about 500 to over 12,000. And these are approximate numbers, you know, so I'm not going to put greater than or equal to, because it's just a rule of thumb. All right. The final way that we can classify open channel flow is according to its criticality. And what do we mean by that? We mean if there are waves propagating down the surface of the channel, we want to compare that wave speed to the flow speed in the channel, right? So imagine you've got a river flowing and then somebody plunks a stone into the river, or you go skipping, right? And you create these circular waves that propagate out, right? So those waves have a wave speed associated with them. And the river is flowing at a certain velocity. We'll assume it's uniform velocity. So the ratio of those two speeds determines the criticality. So you can see here, we're imagining that we've got a river. We're looking at the side view now. We've got flow to the left in the channel with velocity v, and we've got a single solitary wave moving to the left with a speed c, the wave speed. So the most basic definition of the Froude number is that it's the channel flow speed over the wave speed. And so you've got this classification down here. If the speeds are the same, it's critical flow. Okay. If the Froude number is less than 1, so the channel flow speed is less than the wave speed, which is the normal, usual situation. Usually waves on the surface propagate much faster than the flow speed of the channel or the river or whatever. That's subcritical. But if you have a Froude number greater than 1, you've got supercritical flow. And this is an unusual case. And I'm just going to say fast flowing water because usually we're talking about water, but of course it could be another liquid. So I don't know if any of you got a chance to look at this week's module yet, but the discussion question is about hydraulic jumps. And so a hydraulic jump is when you've got the flow in a channel and all of a sudden it goes from one height to a much higher height all of a sudden, right? It doesn't happen gradually over time. You just get this discontinuous jump in height. Looks sort of like a step function, but a little bit rounded out. And that happens when you have supercritical flow, and that flow has to meet a downstream condition quickly, right? It doesn't really have time to accommodate, let's say upstream flows really fast. You've got flow exiting some kind of tank, so that flow rate is set, and somehow the downstream velocity has to be very low, but your channel is not long enough for that to happen naturally. So you get this hydraulic jump in order to dissipate energy, right? So we'll just say hydraulic jumps can occur, and we'll be talking about hydraulic jumps in the next lecture. All right, so we can actually calculate the wave speed on the surface of the water if we make certain assumptions. So if we look here on the top left, we've got a still channel. If you've ever been in the basement of Norris Hall, we have one of the largest water tunnels on the East Coast. It's 96 feet long, and it's just a still body of water, but there's a plate at the end that can move, that can create waves. So if you imagine this plate moves just one time into still water, and you get a single solitary wave with speed c speeding to the right, right? So if you're a stationary observer and you're looking at the wave speed, the water to the right of the wave is going to look stationary, and to the left it's going to have this velocity delta v. We don't know exactly what it is. If you then move over to the right and you start moving with the wave, so now you're in a frame of reference where you're moving with speed c, the wave speed, now the wave looks stationary. You see a fluid velocity ahead of the wave with a magnitude c going to the left, and behind the wave you see a velocity with magnitude minus c plus delta v, right? And why would we want to do this? It seems a lot more complicated. The reason is, if we're over on the left here, that's an unsteady flow scenario, right? You're standing there, you're right by the plate, it creates a wave, something happens and then it dissipates, right? But we want to be able to apply all the tools we've learned already, like control volume analysis. And so that's why we go into this frame of reference where we're traveling with the wave. And so we do that, we put a control volume around the wave with this dashed line, and then we can apply our control volume analysis. Okay, so now if we assume that the flow is steady and one-dimensional and uniform, and I'm just writing 1 capital D for 1D, the continuity equation gives us the following. By conservation of mass, we've got minus c, yb. Now c is the wave speed, y is the depth of the water in front of the wave, where the wave hasn't reached yet, and then b is the width of the channel. Equals minus c plus delta v times y plus delta y times b. We can simplify that, rewrite it, solving for c. We get y plus delta y times delta v over delta y. And then finally, let's make the small amplitude wave assumption that says delta y is much, much smaller than y. So then this simplifies to c is equal to y delta v over delta y. And this is equation 10.1. Now we apply the momentum equation. Form 522. And that gives us, now note that x is to the left here. So positive x is going to the right, and that doesn't quite match with what you might think from looking at this axis, although there's no arrow there. Okay, if we do that, we get 1/2 gamma y squared b minus 1/2 gamma y plus delta y squared times b equals rho b c y c minus delta v minus c. Where m dot is rho b c y. So what is this here? This is the hydrostatic force at section 2 in the figure. It's the pressure. And because we're moving in a frame of reference and we've got open channel flow, it's a reasonable assumption to say that the only pressure experienced at that section is the hydrostatic pressure. And then this is the momentum flux across the control surface. Yeah. All right, if we go ahead and make that small amplitude wave assumption again, that delta y is much, much less than y, then we are left with delta v over delta y is equal to g over c. And this is equation 10.2. So 10.1 is what we get from applying conservation of mass. 10.2 is what we get from applying conservation of momentum. If we now combine these two, we get c is equal to y delta v times delta y is equal to y g over c, which gives us c squared is equal to y times g, which gives us the form of the equation that we're familiar with, that we use all the time, that the wave speed c is equal to the gravitational constant times the depth of the water square root. And this is equation 10.3. And I'm gonna put a red box around that as well, because this is a really important equation. arguably the most important equation in open channel flow, although there are a couple other important ones. All right, so that's how we get the wave speed. And it depends on the gravitational constant and the depth, right? So we see that the main effect is the gravitational force, the acceleration due to gravity. Let's talk a little bit about Froude number effects, just to get some intuitive feeling for what it means to be subcritical, supercritical, etc. So here we've got 3 scenarios that we're looking at, and these are all from a fixed observer's perspective. So in the first case on the bottom, this is subcritical, right? The Froude number is less than 1. And when that happens, when the Froude number is less than 1, it means that the channel flow velocity is less than the wave speed, and that's normal, right? But if you think about it, here we've got the channel flow to the left with a velocity v, and we've got the wave speed in the opposite direction with a velocity c. What a fixed observer will see is a wave propagating to the right, not at speed c, but at speed c minus v, right? Because the flow of the overall body of water is going to slow it down from the perspective of a fixed observer. So the wave travels to the right with a speed c minus v. All right, now the middle case, moving up 1, is the critical case. And that means that the Froude number equals 1. And of course, that means that the channel flow speed and the wave speed are the same. But of course, here, the wave is propagating in the opposite direction as the channel flow. So that means a stationary observer is going to see a stationary wave, right? It's trying to travel this way, but it's being carried the other way at the same speed. So it's just not moving. And then finally, supercritical. So again, this is that case where the unusual case where now the channel flow has just as high a speed as the wave speed, right? So now, interestingly, if you look at this top figure, before we had the channel flow to the left, wave speed to the right, now that wave that's trying to go to the right is getting washed downstream in the other direction. It's getting washed to the left. And it travels with the speed v minus c, right? So just a little sort of intuition building about channel speed versus wave speed. All right, so here we go. We got 2 examples today. And the first example is, imagine you have a tank of water and you've got waves on the surface of the water and they're traveling at a speed of 2 meters per second. If we were to take the tank and accelerate it in 2 different ways, what would the wave speed be? How would it affect the wave speed, right? So first scenario is scenario A. Now the tank is in an elevator going downwards at an acceleration of 4 meters per second. How does that change the wave speed, right? So now you've got acceleration in the same direction as the gravitational acceleration. Does it add or does it subtract? Scenario B is, what if the tank, we still have gravitational acceleration pointing down, but what if the tank were accelerating horizontally at a rate of 9.81 meters per second squared? So the same as gravitational acceleration, but now in the horizontal plane instead of vertical, or in the horizontal direction instead of the vertical direction. So how would that affect the wave speed, right? So I want you to take a minute and think about which scenario, A or B, will result in a higher magnitude wave speed, right? So we know our governing equation for all of this is that C is equal to the square root of G times Y. So C, the wave speed for these surface waves, equals the square root of our acceleration times the depth of the fluid, right? Let's leave that aside for a moment. Just intuitively, which scenario do you think is going to lead to faster wave speed? The scenario where you have waves traveling to the right with a speed of 2 meters per second, and then you put it in an elevator traveling down with an acceleration of 4, or the scenario where you have waves traveling to the right and then you accelerate the tank to the right with an acceleration equal to the acceleration of gravity, right? So I'm going to go ahead and stop sharing for a moment. Bring my toolbar back. So we're going to stop sharing. I'll ask you to think about that individually for a moment, whether you think you'll have a greater wave speed if the tank is in an elevator accelerating down, or if it's on a cart accelerating to the right. And now I'm going to put you guys in groups, and there'll be a poll at the end, like usual, and you're just going to have 4 or 5 minutes to discuss which scenario you think will lead to a higher wave speed on the surface of the tank. So here we go. All right, so it's going to be about 5 minutes or so that if you're watching this recorded video from home after the lecture, it's going to be about another 5 minutes that the students break out into small groups and think about this question. If you have a tank, under which scenario do you have a higher wave speed for the surface waves, right? Whether it's accelerating down in an elevator with an acceleration of 4 meters per second squared, or if it's accelerating to the right with an acceleration of 9.81 meters per second squared. So just, you know, before we learn it, before we really are responsible for knowing this content or being able to answer this question just intuitively, what do you think? We've got about 3 or 4 more minutes that the students will be in breakout rooms. Hey, Matt.
Yep.
What do you think? Do you think that we'll get a higher wave speed when it's accelerating down or to the side?
I'm gonna go with down.
Okay, okay,
That's what our group came up with.
okay. So when it's accelerating down, it has an acceleration, additional acceleration in the same direction as gravity. And then the question is, does it add or does it subtract?
Yeah, that's what we were debating over.
So if you think about it, normally when you're not on an elevator, you're being pulled down toward the center of the earth with some force that's proportional to the acceleration, right?
Mhm.
If you're already accelerating toward the center of the earth, is that the question is that force higher or lower? All right, I'm going to invite everybody out of the breakout rooms now. Thirty seconds. All right, we've got almost everybody back. Welcome back. The last few stragglers have got 9 seconds left till their breakout rooms close. And here we go. All right, so welcome back, everybody. All right, so let's launch a poll and see what everyone thought. Okay, can everybody see the poll?
Yes.
Great, thank you. This is the first poll where the two answers as they're coming in, the two choices are pretty evenly matched. So that means that it's the right level difficulty of question. All right, I've got 92%. I don't usually get more than that. Oh, it just popped up to 96% voted. So I think that's everyone because the other person who isn't voting is the annotator. So I'll end the poll and share the results. All right, so this is really interesting. As I said, it's the first time that the two possibilities or several possibilities were so closely matched. And it's kind of really hard to know intuitively which is the correct answer. So it actually turns out that the more popular answer here, acceleration sideways, is the correct answer. And so we're going to see why now. So let me go back to sharing on the annotator and we'll work through the problem. Okay, so now waves are observed to travel at a speed of 2 meters per second. So we can use that, right? We know we want to use the equation C equals the square root of gy, but we don't know what y is, right? So we can use this information that the wave speed is 2 meters per second to back out what the depth of the water is for this problem and then move forward into solving for scenario A and scenario B. So 2 meters per second squared, as we were given, divided by the acceleration due to gravity, gives us about 0.4 meters of depth in this tank. All right, moving on to scenario A. Tank is accelerating down with A equals 4 meters per second squared. So here we want to find what the effective gravitational acceleration is, right? So the G effective is going to be 9.81. Now, if you're on the surface of the Earth and you're experiencing a force due to gravity downwards, an acceleration of 9.81 meters per second squared, then you step onto an elevator and now you're moving in that direction. The force due to gravity that you're going to experience is going to be less, right? Because you're already moving that direction. So the G effective is 9.81 minus 4 meters per second squared, which is 5.81 meters per second squared. So in this case, our C effective, the effective wave speed, is the square root of G effective times Y is equal to the square root of 5.81 meters per second squared times 0.408. It is 1.54 meters per second. All right, what about scenario B, where now the tank is accelerating sideways? All right, so same approach, G effective. This time it's going to be 9.81 squared plus 9.81 squared, right? So the magnitude of the effective gravitational force is larger, right? So as you can see, what's emerging in this problem is that we treat the gravitational acceleration sort of in a vector sense, right? We think about what's happening in each direction and treat it that way. So this gives us 13.87 meters per second squared, which you can see when we go ahead and now plug that back into our equation that gives us the wave speed. We get a higher answer, right? So we get 2.38 meters per second in the case where the tank is accelerating horizontally to the side. All right, any questions about that?
Yeah, I have a question, Dr. Staples.
Sure.
Why in part A did you subtract the 4 from the G effective? Then in part B, you did the square root?
Yeah, that's a great question. So in part A, you have the two accelerations acting along the same axis, right? But one is being subtracted from the other. One is making the other one less, it's mitigating the other one, right? Now in part B, we have another component. We have another component of the acceleration, right, in the vector sense. So when we want to find the vector magnitude of this force, we have to square up the individual components and take their square root, just like you would for any vector. You know, here the actual acceleration, right, we've got downwards due to gravity in part B, and then we've got to the right due to the tank accelerating. So the actual acceleration vector is pointed downwards at a 45-degree angle, right? We want to find its magnitude. So we have to square up both components, take the square root, whereas in part A, both were in the vertical direction, but one was effectively pointing down and the other was effectively pointing up. So we summed those up first in the vertical direction. And then you can think that we squared the vertical and horizontal components and took the square root, but the horizontal component was just 0 in that case.
Okay, that makes so much more sense. Thank
Okay,
you.
good. Got another question. Does the observed travel speed of the wave not affect C effective, assuming Y is already known? Yes. So, okay, so Lath is asking, did the observed travel speed of the wave not affect C effective? So in this problem, we're saying, first, we've got a tank that's not accelerating, and we observe a wave speed of 2 meters per second, right? Then in part A, we accelerate it down, and in part B, we accelerate it to the right. And the reason that we do this first line before we get to A or B is just to figure out what the depth of the water is in the tank. Does that make sense? All right, any other questions on that example?
Yeah, I have a question real quick.
Sure.
Would we ever get a problem where it moves like in the Y direction and the X direction so that like if that did happen, would we do what we did in part A, like for the Y component of part B?
So you deal with it like you're dealing with finding the magnitude of a vector. So in part B, we don't have motion in the vertical direction, but we have acceleration in the vertical direction, right, due to gravity. So you really did have an acceleration component in the horizontal and vertical direction. So in your case, you would treat it, if you had motion downwards, then you would, if it were constant motion, it wouldn't contribute, right? If it were constant speed, that means there's no additional acceleration, right? But if you had additional acceleration downwards, then you'd subtract that from G. If you had acceleration upwards, then you would add that to the value of G.
Okay, that makes sense.
Yeah. You think about it. Imagine yourself in an elevator, right? If you're sort of accelerating upwards in the elevator, you can imagine that you're going to feel that you're experiencing more force due to gravity, right? But if you're accelerating down in an elevator, you feel less force. All right,
Okay.
any other questions about this problem? All right, let's move on to our second example. All right, this is a really interesting one. So maybe you've seen a scenario like this. I grew up in New Jersey, kind of a coastal state, went to the beach all the time. And when you are at the beach, right, you've got waves that come in from really far out in the distance where the water is deep, and then they approach the beach, and then eventually they break at some point as the beach gets really shallow. Here we're talking about a situation where you can see that the waves far offshore are coming in at an angle, but they somehow sort of seem to magically turn and break perfectly horizontally aligned with the beach. And the question is, well, why does that happen? You know, how can this be understood, this phenomenon of the wave sort of turning so it approaches and breaks evenly, parallel to the shore? Well, we can actually think about this just using the same equation that the wave speed is equal to the square root of G times Y, the depth, right? If we pick one wave here, this one, and label the far end 0.1 and the near end 0.2, we've got some depth associated with end 1 and some wave speed there, right? Here we've got a different depth and a different wave speed, right? So what do we know? We know that the farther out you go from the shore, the deeper the water gets, right? So we know that Y1 is greater than Y2, right? So if even on the same wave, because it's angled, this end labeled 1 is farther from the shore, and so it's experiencing a deeper depth on average, right? Usually. End 2 is close to the shore, so it's at a shallower depth, right? So the depth at the one end is greater than the depth at the two end. Then, because our wave speed is proportional to the square root of the depth, this means that the wave speed at the end labeled 1, the far end, is higher, right? So this is going to be a higher magnitude wave speed. So then what happens is it's coming in like this, but that side of the wave that's farther back has a higher wave speed, so it accelerates forward and catches up to the near end, and that has the net effect of making the wave straighten out. Right, and that's because the wave speed is proportional to the depth. So, any questions about that? Does that make sense? I kind of like that even this, very fundamental, simple equation of open channel flow can explain phenomena like that. All right, we're doing really well on time. Let's skip ahead to our final slide. All of your video projects have been approved. They were all great proposals. They've all been approved. A couple of them I gave comments saying, if you run into trouble trying to do this, maybe you can try this instead, but they were all just really solid proposals. Unfortunately, Hyung-gun is still grading partial credit for midterm 2. He said it's a little harder to grade, and also he had a midterm last week, so he didn't get to it as quickly this time. Wednesday, we're continuing open channel flow. We'll talk about hydraulic jumps, which if you haven't done the discussion question for this week yet, you should do it. It's not answering a question verbally. It's going to your kitchen sink, turning on the faucet, and making a hydraulic jump, taking a picture and uploading it. And then here's the list of problems that Hyung-gun will go over on Friday. They're very similar to your homework problems. Quiz and homework 11 due on Sunday as usual. Any questions? No? All right. All right. Well, wonderful. Thank you very much, everybody. Let's end here 1 minute early, and I will see you guys on Wednesday. Have a great week.
Thank you. Have a good day.
Thanks, you too.
Thanks.
Thank you.